Now we're going to work with some applications in economics where we want to use this knowledge that we have on exponential and logarithmic functions. Before we look at some examples, we first need to understand discounting. And what you'll see is that discounting is the reverse of interest compounding. So to remember what interest compounding is, if we have 100 Rand at the beginning of a year, right, and we invest it at 6% interest for 1 year under annual compounding, then the value of that investment at the end of year 1, right, can be calculated using the formula that we learned earlier, and we can see that that 100 Rand will be worth 106 Rand. Okay, so discounting is the reverse question, right? And what the question that we are asking is, what is 106 Rand occurring in 1 year's time worth to me today? So in other words, what is the present value of that 106 Rand in this example? Okay, and we already know the answer because we have the figures, but the value of 106 Rand accumulated in 1 year, or in year 1, is worth 100 Rand today in year 0. All right, and we would work that out with this formula here. 106, which is the value at the end of year 1, 1 plus the interest rate, which in this example is 6%, so it would be 1 plus 0.06, okay, and that would give us a present value of 106 equal to 100 Rand. If we want to express our formula in more general terms, this is what it would look like, okay? So I've rewritten the numerical example from the previous slide at the top of this slide, just so that you can remember. And if we wanted to work out a more general formula, what we would have to do, the calculation would be the present value of the investment at the end of 1 year, okay? In this example, we're looking for the value of the investment at the beginning of year 0, okay? That's the present value, all right? And the way we would work that out, it would be the value of the investment at the end of year 1 times by, and then in brackets here, we've got 1 plus the interest rate, and this bracket here raised to the power of -1. Okay, so it's very similar to what we saw here. The only thing is we have taken this bracket out of the denominator, brought it up to the numerator, but then obviously in doing so we need to raise it to the power of -1. All right, so this is for the present value of a sum that is invested for 1 year. All right, for t periods of time, okay, if we want the present value of an investment after t periods of time, okay, we would need to take the value of that investment after t periods and then multiply it by 1 plus the interest rate, all in brackets, raised to the power of -t. Okay, and this here, 1 plus I raised to the power of -t, we refer to as the discount factor, and I we refer to as the discount rate. In our previous example, we were working with interest being added only once a year, so annual compounding. But recall that when we were examining the process of interest compounding, we spoke about interest being continuously added, or put differently, the case of continuous compounding. So if we now want to take a look at discounting, where we have continuous compounding, we need to first of all recall how to calculate the future value of an investment after t years when we have continuous compounding. And you will recall that we had a look at this formula here, where we take the initial value of the investment, the principal amount, okay, V0, and we multiply that by E raised to the power of R times T. Okay, so this is when we are trying to calculate the future value of an investment after a period of time, T. So if we want to do the opposite now and work out the present value of VT. So if we know what the value of our investment is after T years, and we want to discount it, in other words, we want to work out the present value of that amount. Okay, we want to work out the present value of VT, which is our amount in the future. Working with this formula here, just changing things around a bit, you can see that V0, which would be the present value of VT, we would work out by dividing VT by E raised to the power of R times T. Okay, or writing it differently, bringing E into the numerator, but then we obviously have to raise it to minus RT. Okay, so this formula here would enable us to calculate the present value of VT, which is our amount from the future, if you like, okay, when we have a process of continuous compounding, when interest is being continuously added over T time periods. Okay, and here E raised to the power of minus RT is the discount factor, and R is the interest rate. Okay, so now that we understand discounting, we can use our knowledge of discounting as well as our knowledge of working with exponential and logarithmic functions to answer problems, economic problems related to optimal timing. Okay, so if we just take a look down here, the process of discounting is important because maximization problems can be applied to calculate the maximum present value of something that is rising in value through time. For example, a rare piece of art. So here we have an example. All right, we have a piece of art and it is known to be rising in value, V, okay, according to the following function. Okay, so the art's value after T periods is equal to K times E raised to the power of square root of T. Okay, so there will be an optimal time when the owner of this piece of art should sell. And this is the question that we want to answer. What is the optimal time at which to sell this piece of art? So, if we were to sell this right now, all right, then the value of the piece of art would be K, okay, because the time period would be 0, okay, in other words, the owner of the piece of art would not hold on to it for any period of time. They would sell it right now. Okay, so this here would be 0. Okay, anything raised to the power of 0 is 1. So the value of the piece of art, if it was to be sold right now, would be K. All right, so if we wish to sell the asset, the art, at some point in the future, then we will wish to maximize the value assessed in today's terms. Okay, we want to maximize its present value. All right, and we will need to know the discount rate to make this decision. All right, so we want to maximize the present value of this piece of art. Okay, and recall that the present value, all right, if we calculate the present value where we have a process of continuous compounding, okay, can be calculated using this formula here, okay, just set out slightly differently. In applying it to this example here, where VT is given as follows, okay, we can substitute this into our formula. All right, so we substitute in for VT, substitute in for VT. What we need to remember is that we are looking at the present value of this asset. So we want to work out optimal timing, the time to sell this asset, based on the present value of this asset. We don't want to work with the future value of the asset, because obviously there will be very different values for this asset in the future depending on what time period we are looking at. So if we want to compare the value of this asset, then we need to bring all these future values back to the present point in time, i.e. work with the present value so that it is easy to make a comparison and thereby work out the best time at which to sell the asset. Okay, so in determining the optimal time, we are going to maximize the present value function with respect to t. Okay, we're not going to maximize the future value, okay, function with respect to t. Okay, it's quite important that we remember that distinction there. Okay, so our first order condition, which we'll see on the next slide, is going to work with our present value function. Okay, and a way that we can think about this is, given R, okay, given the discount rate, how many years should we hold onto the work of art before we sell it? Okay, so we need to find the value of t, the time period, that is the optimal time period at which to sell our work of art, okay, and we will have a maximum value in terms of present value. The first order condition is then to take our present value function, differentiate with respect to t, and set it equal to 0. Okay, this is going to help us work towards identifying the optimal time at which to sell our asset. Okay, so let's take our present value function that we saw on the previous slide, and here it is rewritten here, and it's an exponential function as we saw. All right, so we had it in this form here, and using one of the rules of exponents, okay, it's where we have two numbers where we have the same base multiplied together, and we just have different exponents. Then we keep the base and add the exponents together, and that's exactly what we've done here. We've got e here and e here, so now we have one e and we have added the exponents together. Okay, so this is now our present value function that we're going to work with, and our starting point is going to be to take natural logs. Okay, remember we need to differentiate this with respect to t, time, and we saw earlier on in the session that taking natural logs can really make it easier to differentiate. So if we take natural logs of both sides, okay, so we have the natural log of PV on the left hand side, and on the right hand side we can simplify somewhat. We've taken the natural log, but here we've got k times e raised to this power. So using our rule of logs with respect to products, okay, we can rewrite this as the natural log of k plus the natural log of e raised to all of this here in the exponent. And then recall the natural log of this expression here, okay, e raised to this power here, the natural log of this entire expression here is going to be what we have in the exponent. Okay, so we can rewrite this as follows, and then in the very last line, instead of having the square root of t, we raise t to a half, the power of a half, just a slightly different way of writing that. We now need to differentiate both sides with respect to t, so both the left-hand side and the right-hand side. The left-hand side, when we differentiate with respect to t, we will end up with 1 over pv times by dpv over dt. The right-hand side, when we differentiate with respect to t, okay, we will be working with these two terms here because this first one here does not contain t. Differentiating here, we will end up with a half t raised to the power of minus a half, and here we will get minus r. Okay, so that's the right-hand side differentiated. We can now set the left-hand side equal to the right-hand side, and then isolating dpv over dt, on the left-hand side, we would need to take pv across to the right-hand side. In other words, multiply both sides by pv. Okay, and there we have dpv dt. Working out which t at which pv is maximized, we need to set what we have calculated above equal to 0. Okay, that there is our first order condition. Okay, setting dpv over dt equal to 0. All right, so first of all, we just need to see we have pv here, which is present value. Now, this is always going to be positive. It's an exponential function. Okay, so we're going to ignore pv, and we're going to focus on what's in the bracket, okay, where we've got t and r. All right, and we want this to come to 0. All right, so if we set all of this equal to 0, all right, and then solve for t, all right, which is just a little bit of calculation, we can see that t equals 1 over 4 times r squared. Okay, so what this is now going to enable us to answer, the question that we can answer is, depending on what the interest rate is, okay, or the discount rate, depending on what that is, we can now work out the optimal time, okay, the best time at which to sell our work of art. Okay, so if we read what's in the box here, if the discount rate is 10%, then t equals 25 years. That's when we should sell the work of art. If the interest rate is 8%, then it's longer, 39.06 years. The lower the discount rate, okay, the longer you will hold the work of art. Okay, so we are nearly at our final answer, but there's one more thing we need to address. Will this indeed give us a maximum? So using our first order condition on the previous slide, we were able to calculate a t, a time period that we should sell our work of art. But now we need to ascertain whether this will be the optimal time period. And to answer that question, we now need to check the second order condition. So we take dpv dt as we calculated it on the previous slide, and we now need to work out the second order condition, and we do so by differentiating again with respect to t. Okay, so we're going to differentiate this again with respect to t. And we'll use the product rule because here we've got our present value function multiplied by what we have here in the bracket. Okay, so if we use the product rule of differentiating, okay, if we leave this function in its original form and then we differentiate PV with respect to T, okay, we set it out here, plus now we leave PV in its original form, and if we differentiate what's in the bracket with respect to T. All right, so we now need to work through these calculations, but first let's just note that at the optimal point, okay, dPV dt will be equal to 0. Okay, so this whole term here will be equal to 0. Okay, so working now with this second term, all right, remember now we need to differentiate what's in the bracket with respect to t. We leave PV in its original form and differentiating with respect to t, okay, we would take minus a half times a half, we'll end up with minus a quarter, and in the exponent we'll end up with minus 3 over 2, and this term r does not have t in it, so it would be equal to 0 if we wanted to differentiate with respect to t. Okay, so here we have our second order condition, or after having differentiated. So if the time period that we have calculated is indeed going to maximize the present value of our work of art, or selling at that time period is going to maximize the present value of our work of art, then we need this second order condition, we need all of this here to be negative. Okay, we recall from topic 7 that this needs to be negative for us to have a maximum. All right, so if we look at PV, the present value function, this is going to be positive. Okay, it's a positive, it's an exponential function. All right, so we don't need to consider it. And then what we have left is what's in the bracket, and we can very clearly see that with a negative sign, it is less than 0. So we do have a maximum, and what that is telling us is that the time period that we have identified, if we sell our work of art at that time period, then we will maximize the present value of our asset.